Yeah, in general, permafrost, it's a topic that often people think, oh, it's a very far away. I don't live on permafrost. But it's a topic which is of concern, or should be of concern for all of us, because we have more than 20% of the northern hemisphere being underlain by permafrost. So there's so much carbon there in the ground, which will be released in the future due to the warming of the ground. So it affects everyone.
Hi, I'm Stephanie Tumampos, and you're listening to Down to Earth, the show where we talk to incredible geoscientists about their science and its impacts on our planet. This season, we're exploring stories of resilience, hope, and scientific insight into climate change. We all know the Arctic is warming rapidly. This is affecting sea ice, marine life, and permafrost. But what you may not realize is that permafrost thaw is directly related to the amount of methane released into our atmosphere, both from natural Arctic wetlands as well as human-based sources. Today, we're talking about what this means for our planet and what scientists are working on to collect information about methane release that will be critical for our efforts to address climate change going forward. This episode of Down to Earth is brought to you by the Remote Sensing Environment Analysis and Climate Technologies, or REACT Technical Committee of the IEEE Geoscience and Remote Sensing Society. The REACT Technical Committee is a collaborative and supportive venue for all scientists and engineers looking to exchange ideas and share knowledge that advances our efforts to tackle climate change. To learn more and be part of this incredible cutting-edge community, visit grss-ieee.org and select the REACT Technical Committee.
So we have permanently frozen ground, permafrost, on the northern hemisphere as well as on the southern hemisphere. On the northern hemisphere, it's approximately 25% that is affected by permanently frozen ground, and 20% of the surface, which is actually underlain by permafrost. It's very difficult to quantify this. And then on the southern hemisphere, we have permafrost in some of the mountain ranges, even in Africa, and some parts of Antarctica, which are not covered by ice sheets. We find permanently frozen ground.
This is Dr. Annett Bartsch. She's the founder and managing director of an Earth observation company called BGEOS. Through this company, she uses satellite technology to study how permafrost thaw is changing our landscapes and our climate.
What we see from the satellites, it's featured of the surface, or maybe something within the atmosphere. But for permafrost, we need information from below the surface. And that's really tricky to get from satellites. In general, we cannot get this information. So what we are looking for kind of proxies, something what drives the temperature in the ground.
Annett has spent several decades studying permafrost, so she has a ton of knowledge to share with us today. Let's jump right in. Welcome back to the podcast, Annett. Happy to be chatting with you again.
Yeah, so hi, Stephanie. Nice to see you.
Now, we've done a previous episode on permafrost, but for those who haven't heard that episode, let's start with some basics. What exactly are we talking about when we say permafrost?
Permafrost is permanently frozen ground. So it's actually defined by temperature. So anywhere where we find temperatures below 0 degrees Celsius for, by definition, at least 2 years in a row, that's permafrost. So we find it in very cold regions across the Arctic, but also in the high mountain areas.
Now, in the past, you mentioned that it's difficult to study permafrost. What parameters are we looking at for permafrost monitoring?
We are primarily looking for temperature. So what's the temperature in the depth in the soil? We are not primarily looking for ice, because it's not really necessary that there is ice present to have permafrost. Of course, it is in many cases there in the pores of the soil, but primarily we are measuring the temperature in the ground. And that's rather difficult because you need to make a borehole and then measure in the depth. So the ground is thawing on the surface every summer. So the surface is by definition not permafrost.
In Season 3, you talked about how subground temperature and active layer thickness are permafrost parameters that cannot be observed from space. So what are some of the different ways we use remote sensing to study permafrost thaw?
So what we are looking for kind of proxies, and then we combine this information with models, or we try to establish relationships between subground temperature and other parameters observable at the surface. And then from that way, we estimate what is the temperature in the ground. So that's one of the ways how we try to address permafrost monitoring on a global scale. And then there are also a number of surface expressions which tell us, okay, there is actually a permafrost below. And these surface expressions, they are usually related to changes in ground ice content. When permafrost is degrading, so when it thaws, then the ground or the ice melts in the ground. It might flow somewhere. And then the ground on top is subsiding because there's some volume missing. And this is something we can observe from space. And then these terrain changes, they reshape the landscape and they change how water flows. So you might have lakes appearing or disappearing, or you may have general changes in soil wetness, what then allows certain or changes the type of vegetation, what is growing on top. And that's all things that we can see on the surface. It's processes which are rather slow. This means we need really long time series. We try to look back in time as far as possible. What is, of course, well, there are limitations to that using satellite data.
How does looking at time series of permafrost help with studying permafrost with satellites? And you mentioned about these limitations. What are our limitations?
Yeah, the landscape in the Arctic is extremely heterogeneous. So we see these changes related to permafrost. They are usually related to land surface hydrology or microtopography changes. And we have small lakes which appear or disappear, and they are really small. So almost everything what we are interested in this context is really small. So we need a very high spatial resolution. And these type of data, first, they only became available recently. And then the second thing is it's only available over smaller areas and not for the entire Arctic in regular intervals. So that makes it very challenging. So there are satellites which tell us something about vegetation going back into last century, when they have a really coarse spatial resolution. So we might see some changes in these pixels, but those are mixed pixels. So if we observe a change, we cannot really say, where is it coming from? Is it coming from a lake change? Is it coming from a vegetation change? So people still try to use these rather coarse spatial resolution data to go back in time because there's not really something really better available. But then you have to be very careful in how you interpret the trends. A good coverage of that started around 2000. Before there was Landsat, but it's a bit patchy. So the main source has been actually Landsat for these type of studies in the past. Now people start to change to other like Sentinel-2 from the Copernicus missions, because it's with 10 meter, it makes a big difference. 10 meter compared to 30 meter. In Arctic landscapes, it's really a big difference. But it's still not yet sufficient.
And I assume with the lower resolution data especially, you have to verify what you're looking at by checking the ground truth, right?
Yeah, it's really important to go to the field and to see what is in my mixed pixel. And to see, you're specifically looking for degradation features, so some changes in the terrain. Of course, then it is important to go there for several years in a row, maybe, so that you see something developing. That's the ideal case. To some extent, it has been documented, maybe in some older fieldwork by someone else. But also we can see these areas which have changed in the past. So you actually can see this usually in the landscape. And working together actually with geomorphology experts and permafrost in situ experts, it's really important to gain this understanding of what we actually see in our pixels in the satellite data.
Based on your decades of experience, what trends are you seeing with respect to permafrost thaw?
Yeah, what has been shown in several regions of the Arctic is that we see quite some impact due to extremes. and extremes in the meaning of hot summers. So if we have like heat waves and unusually warm conditions, that's warming the ground. So the surface is warming more, and the what we call the active layer, so this unfrozen part on top of permafrost, it's getting deeper. It's in the order of several tens of centimeters to meters. And as it's getting deeper than in years before, it may start to reach soil layers which have more ice. And then when this ice melts, well, it's liquid in the soil. If it's on a slight slope, a very slight slope is sufficient, it can destabilize the ground and we have a landslide. And with satellites, we have identified several hundreds or thousands of them being active across the Arctic. So there are really many of them. And we know by now that they are triggered by these exceptionally hot, warm summers. And then we also can use temperature from the land surface that can be observed from satellites. And what we could show is that the temperature in the northern hemisphere has been increasing in the ground by 1 degree Celsius since 2000. And that increase actually with in situ measurements. So we know from the boreholes, it's only very few spots where you have really good time series where you can see these changes. But all across the Arctic, they show the same signal.
You've also been doing research on rain-on-snow events. What role does this activity play in permafrost thaw?
Yeah, so rain on snow. So this means liquid precipitation in winter. So these raindrops, when they touch the surface of the snow and they percolate into the snow, it's warming. So you have temperatures around 0 degree in the snowpack. And it's been shown that it's warming the ground, and not just in this very short moment when it's raining, when this water has not yet been refrozen. It's also over the remainder of the winter. It may not have a big effect, but we have many regions across the Arctic where we have rain and snow events in winter. And that's an effect which adds to the general warming of the ground. And these rain on snow events, they are predicted to become more frequent across the Arctic.
You said these are becoming more frequent, these rain on snow events. Is this because of climate change?
Yes. And there are some theories that they relate to ocean properties, especially sea ice. So they often occur in early winter. So in November, for example, we have sometimes the sea ice in the Arctic is not yet completely frozen up. So we have some ice-free areas still. So some of it might relate to that. But actually, for the time where we have satellite records or satellite products available for detecting rain on snow events, we do not see trends. But we have been able to document extremes. We have been able to document, for example, 2 years ago, there was in Alaska, in the region, a really big rain on snow event, which was the only one within the 20-year time series that we have been looking at. And it was had quite some impact also on wildlife. So we are able to document these type of events nowadays well with satellite data, but it's not really so clear, or we do not really see these clear trends like we see them for ground temperature.
Mm-hmm. Now, this episode is about permafrost and its connection to methane. So tell us, in your view, what's the connection between the two?
Yeah, so the important point here is that we have a lot of carbon frozen in these soils in permafrost. This carbon it has been accumulating there a long time ago, between before the last glaciation in the interglacials. That's quite old carbon. And this carbon becomes available for decomposition. It becomes available for decomposition by microbes when the temperatures are increasing, when the ground is thawing. And that's the big issue here. So this decomposition, it results either in CO2 or methane. And it depends on water, on how wet the soil is. what is happening to this carbon. So if it's dry, then CO2, but if it's wet, we have anaerobic conditions. If the ground is saturated, so it's a wetland, then the release is methane. That's the linkage here. So we have a lot of wetlands in the Arctic on permafrost. And so we know that quite some proportion of this carbon in the ground will go into the atmosphere as methane if the ground is thawing.
Now, we all know CO2 release is contributing to climate change, but methane is potentially even scarier than CO2. Can you briefly explain why?
So the global warming potential of methane is much higher than the global warming potential of CO2. So still some decades ago, people were talking about the global warming potential of 23, 24, so that it has 24 times higher global warming potential than CO2. And this number has been increasing actually over the years. We are now by 28. So it has a much higher impact on the warming, and that's the issue.
In terms of natural methane released from permafrost, what are we seeing? Is there a lot of natural methane being released?
Yeah, well, the amount, it's comparably small if we compare this to human release of methane. So if you think about gas fields and what is actually coming out there by accident or due to transport of methane, it's very difficult to measure it from space, really difficult because the quantities are so small and it's not point sources. But if you do this in the field, in situ, you do this over only a small area. And in order to have this idea about what's the overall amount over the entire Arctic, you need to upscale. What you do, you link it to a land cover map. The land cover type that we are looking for here, it's wetlands. So what we need is a good wetland map for the Arctic to be able to upscale these in situ measurements and then to provide a number.
And to my knowledge, we don't yet have a clear understanding of how many wetlands exist in the Arctic, right?
Yeah, actually, I can't really give you a number of how many wetlands are there because the question is, how do you define a wetland? And this is still something what we need to work on. Actually, this is something what we are currently looking into. You can say, okay, it's only areas where you have a flooding, inundation, so standing water. But we know that methane emissions are also very high when you have just a really wet soil close to saturation. So you also need to include this. Yeah, and inundation is what you can see from satellites. But these wet soils, that's a bit more tricky to capture this and to add this to the picture. And then there's the question of seasonality. So you need a really dense time series throughout the short unfrozen season to see whether there is some seasonality, that it's maybe at some part of the year it's dry, or in some part in spring it's wetter. So we have these permanent and seasonal wetlands, and then all playing a different role for the methane release. And that's until now not really fully quantified. So we don't really know exactly how many wetlands are there, but it's a large portion of the land cover which is a wetland. Much more than what you have in these global land cover maps.
Who knew there were wetlands in the Arctic? I sure didn't. But the reality is, between naturally occurring wetlands and ones that are forming due to a thawing permafrost, we're looking at a lot of potential microbial methane release in the future. And of course, natural wetlands aren't the only sources of methane release in the Arctic. Human infrastructure plays an even bigger role. After the break, Annett shares the numbers and some exciting new projects she and fellow Arctic researchers are working on to ensure we can track methane release into the future.
Are you passionate about protecting our planet and tackling the challenges posed by climate change? Do you want to be a part of a remote sensing community that brings together the brightest minds in environmental science and engineering? then you need to check out the Remote Sensing Environments Analysis and Climate Technologies Technical Committee, or REACT-TC for short. Here on the REACT Technical Committee, we believe strongly that interdisciplinary collaboration is key to making a real difference in our world. That's why we bring together experts from various fields to exchange ideas, share knowledge, and advance the science that drives our understanding of the planet. Whether you're a scientist, engineer, or simply someone who cares deeply about the environment, the REACT Technical Committee of the IEEE Geoscience and Remote Sensing Society is a place for you. Together, we can make a difference, one discovery at a time. Visit grss-ieee.org and select the REACT Technical Committee to learn more.
Welcome back. Today we're speaking to Dr. Annett Bartsch, founder and managing director of BGEOS, an Earth observation company based in Austria. Through our conversation, we've gotten a good sense of the ways climate change is impacting Arctic permafrost. We've also learned that higher resolution satellite data is helping us track these changes. But tracking natural methane release from space has proven to be a tad trickier. One place we can see methane release from satellites is from human infrastructure. Let's learn more. Now, you mentioned earlier that methane release from wetlands is very small compared to human-released methane, particularly from the oil and gas sector. So let's talk a bit about human infrastructure in the Arctic. You recently created and then updated the first pan-Arctic satellite-based record of infrastructure along permafrost-affected coasts. Tell us about this research.
Yeah, so in this case, we were actually looking into issues along coasts. And one of the degradation features of permafrost is strong coastal erosion. In general, we have a very high coastal erosion rate. It can be several meters per year that the coastline is retreating. And now there are many people living there, so people are affected by this. And it's estimated that overall, more than 5 million people are living on permafrost. And about 1 million people are living along the coast. And all these settlements, they are affected by permafrost thaw. They are affected by what is happening along the coast. But we are also looking into what is then potentially what can happen due to the general thaw of the ground. Yeah, so we know that the ground temperatures are increasing. We know that this active layer, so the seasonal unfrozen layer on the top, that this is in the depth, it's increasing in many of the coastal regions. So this means if we have a deeper thaw, that this is also a problem for the infrastructure. But until now, we didn't really have a consistent account on infrastructure across the Arctic. Now, with the 10 meter of Sentinel-1 and Sentinel-2, we are able to capture where the settlements are, and specifically related to industry, all the roads related to that, they're big enough that we can capture them with the 10 meter. So our idea or our goal was to create for the first time a consistent infrastructure and settlement and a general human impact data set for the entire Arctic. So we used the fusion of Sentinel-1 and Sentinel-2 using machine learning to identify where are roads, buildings, and also other human impacted areas like open pit mining. There is a lot of that across the Arctic, as we now were able to quantify. Yeah, and all these constructions related to oil and gas industry.
Have the human impact activities like construction related to oil and gas and mining increased? And have you seen changes between when you first prepared this pan-Arctic satellite record and when you recently updated it?
So until now, we have only one recent picture of that. We have one map representing like the last 5 years. Well, we do not have the spatial resolution like from 20 years back. That's something what we can do. We can combine this with coarser resolution information. Because what usually happens is when you build a road or some building, you remove vegetation. And these changes in vegetation, this is something that you can capture with also these coarser resolution sensors. Yeah, you have this 30 meter, it's a mixed pixel. But this removal of vegetation, the signal is so strong that you can identify it. So what we did NDVR. We used the normalized difference vegetation index, so this standard index in remote sensing for looking at vegetation. Applied this to landslide time series across the entire Arctic. And then now we know where is the road now. We know where it's building. So just for these objects that we have identified, we've been looking into their history of vegetation. So if there has been a strong decline in vegetation in the last 20 years, and if this is the case, then we know it's new. And this way, we have been able to identify or to quantify that more than 15% of the infrastructure has been built in the last 20 years.
So that finding that the detectable human impacted area in the Arctic coastal region increased by 15% since 2000, with the majority being attributed to the oil or gas industry, is the most compelling to me for today's discussion about methane and permafrost thaw, because really the link between methane and permafrost thaw isn't just about wetlands and what's released naturally. It's also about how permafrost impacts the oil and gas infrastructures, right?
Yes. So you have to take care about ground instabilities or whatever you built on permafrost. Over most of the areas where we have now oil and gas infrastructure, those are the regions which will undergo warming and thaw within the next decades. They are actually located currently in these transition zones of permafrost. So what we call like a discontinuous permafrost zone, where we have already proportions of ground there which are not permafrost anymore, where we have temperatures rather close to 0 degrees Celsius. So where we know in the next decades, the ground will thaw. So if we just make a very simple assumption that the trends that we have seen over the last 20 years, if they continue, then 50% of what is now still on permafrost will be on thawed ground by 2050. Now, when I'm talking about coastal, our definition was within 100 kilometers from the coast, was quite a lot, and that actually includes a lot of the oil and gas infrastructure.
So we're looking at the potential of a lot of damage to the oil and gas infrastructure. Are we seeing this happening now? Should we be worried about more leaks and methane release from the oil and gas industry?
Okay, there can be different types of damages. So you have like just the road, and then you have the pipeline. And of course, a lot of maintenance is needed for these pipelines. They need to be very well constructed to be prepared for any type of ground thaw. So that's several things to think about. So we hope that the oil and gas companies, that they are really taking care about this so that there are not so many leakages. We know that leakages can happen along the pipelines. There can be various reasons. So some of that can be even observed from satellite. So we just hope that the industry is really thinking about it and that they look into these foundations and that there is some proper maintenance.
I really hope so too. I mean, this is a very dangerous situation if it happens, Now, I said I wanted to get back to wetlands, and this is one of the foci of the AMPAC, the Arctic Methane and Permafrost Challenge. You're participating in this project, so please tell us about this initiative. What are the goals of this research and what progress has been made so far?
So AMPAC is a joint initiative by NASA and ESA. It's the Arctic Methane and Permafrost Challenge. NASA and ESA have founded this initiative together. And what they wanted is to bring researchers with different perspectives, different backgrounds together to tackle all the questions related to permafrost thaw and methane release for Arctic permafrost regions. And it's quite a large topic, I would say. The way how we try to quantify how much methane is released, there are different ways to address this. First, by doing this bottom-up, so you take wetland maps, land cover maps, and you upscale your in situ observations, or you take the satellites and measure this from the concentration in the atmosphere, and then you are trying to make some assumptions about what of this methane in the atmosphere comes actually from the surface, from natural sources, from wetlands. So at the moment, these different approaches, they do not really give us the same number. They're getting closer and closer with integrating more and more data and considering of more processes, but we have not really brought the numbers together yet to match. And then the question is, okay, that would be just quantifying what is ongoing now. But the big question is, what is going to happen in the future? What is going to happen with permafrost thaw? So that's the next thing. And this is like the goals of this initiative that we would like to answer these questions. So first, how much is actually coming from the natural sources in the Arctic? And then how much is released actually due to permafrost thaw? And it's a rather complex issue. So within the next years, we are getting closer to answering these questions. But it's really difficult to quantify this because you need proper wetland maps with a very high spatial resolution that we do not have yet available. And you need really good observations from space regarding methane concentrations that we do not have for the full year yet, and also not at the spatial detail as we would like to have.
So the AMPAC project is asking some pretty big questions about methane and permafrost, and it's bringing together a lot of skilled minds to answer them. That definitely gives me hope. Now, this is a tough question, and you might not have the answer, but are we too late in asking these questions about methane, or do you have hope that we'll find important answers soon enough to respond and create change?
There is potential to improve our estimates. We just need to start looking into this and to start to combining all the resources that we have, the different knowledge that we have across the community, that we combine this and that we can come up with some better estimates. Of course, there are some technical limitations from the satellite side that not be solved very soon, and it takes a long time for satellites to develop, and until they launch, it's really a long time. But now we have the awareness of the issue, and it's really important that we really work on this.
In your view, what are the next steps for research and monitoring of permafrost and methane?
Yeah, so we need to get this circumpolar picture. This is really important. So people have been doing this big picture analysis, but with a really coarse resolution data, but we need to do this in a much better detail. To some extent, we have this data now available with some recent satellite missions, including the Copernicus missions. We just need to work with it. And then there are some really interesting missions coming up next year, which will be very relevant for the topic. So we will get new data in. So that's something that we will certainly work on over the next years.
What's one concrete action you think listeners could do in their own lives, either as researchers or as citizens, to address the challenges surrounding permafrost thaw?
Yeah, so the reason that we see permafrost thawing, it's global warming. So it's connected to all our lives. So we have this increase of anthropogenic emissions, which is causing this. And I think that's something that everyone can do. So we can think about our carbon footprint, for example. So that's something that everyone can do. And from the researcher's perspective, well, of course, it depends what you're working on. But this topic, it needs lots of different scientists involved here. So maybe whatever you're working on, you might actually be able to contribute to some of these projects. So just keep your eyes open for these type of positions, which are hopefully in the next years are upcoming.
In our next Down to Earth episode, we'll be speaking with a researcher who is working on a brand new satellite scheduled to launch in early 2024 that will really build on our ability to track methane release. So be sure to tune in. Until then, check out the work from AMPAC and Annett.
For AMPAC, we have a webpage which is called AMPAC.net. Our company has a webpage. It's begeos.com or begeos.at. And then our permafrost work is part of the ESA Climate Change Initiative.
Follow and rate us on Spotify and Apple Podcasts. We're eager to hear what you want to learn for future episodes. And give our sponsor pages a like at IEEE_GRSS on Twitter and Instagram, and IEEE Geoscience and Remote Sensing on Facebook and LinkedIn. This episode was produced by Nicole Bedford from Nicole Bedford Films, with help from me, Stephanie Tumampos. Graphics and design by Mylene Briggs of Kila Media. And a special thanks to Irina Hansek of ETH Zurich and the German Aerospace Center for her support. I'm Stephanie Tumampos, and you've been listening to Down to Earth.